Stanford University.
Oh, welcome. Welcome to EE 380 Spring 2010-2011. I'm Andy Freeman. The other lecturer for this class is Dennis Allison. We're getting into the quarter, so insert rant about keeping up. As I mentioned last week, today's talk is about a new way to write parsers, to generate parsers. The standard argument for why this is a big deal is that parsers and language theory have always been at the core of computer science, yada, yada, yada. However, with the exception of regular expressions, parser generators rarely aren't used much by people out in the field. And this is odd because they show up in surprising places to great effect. One of my favorite examples is a recommendation site called TechMeme. What does that have to do with parsers? But Gabe Kaplan has used his compiler work to make a fairly interesting site of managing communication and information flow. I think that the overuse of regular expressions shows that there's demand for better parsing tools, and the ease of use of such tools is a key obstacle. Today's speaker, Matt Might of the University of Utah, works on static analysis to improve the behavior of various systems, and is here to talk about parsing with derivatives.
Thank you. So it's kind of odd that in 2011 there's anything left at all to say about parsing, yet here I am. So I don't do parsing for my day job, but about a year ago when I was doing joint work with one of the undergrads at Utah, we stumbled across a way to extend the derivative of regular expressions to context-free grammars and thereby use it to do parsing. So that's what I'll talk about today. But I do have to give you a warning. About a year ago, we submitted this work to peer review and it was promptly rejected. So we do plan to resubmit it, and I'm pretty sure it'll be accepted at some point in the not too distant future. But for the moment, that puts this work in the epistemologically nebulous category of not yet true. But trust me, we've proved it, we've implemented it, we've tested it. It does actually work. But please obey this warning. So I'm assuming most of you know what parsing is. But if you don't, here's my abbreviated tour of parsing. Parsing in general is a transformation from unstructured data to structured information. And within computer science, this typically takes the form of a transformation from a sequence to a tree. So for example, if you wanted to understand the meaning of an expression like x plus 3 times 10, where we're interpreting this at the moment as a sequence of characters, we need to turn this into a tree which encodes the associativity and precedence of this expression. And so that's exactly what a parser does. And so that by the time you've got your tree, if you wanted to understand the meaning of that expression, you could construct something like a recursive tree walk to figure out what it means. And as it turns out, and as Andy mentioned, parsing is ubiquitous. Now, I'm not the first to make this observation. As recently as POP 2010, Trevor Jim was listing all sorts of places where parsing appears in computer science. For example, it clearly appears in places like compilers and interpreters. We all know that. And we have lots of parsing tools for dealing with these situations. It should show up more in syntax highlighting, although it doesn't always show up in places like syntax highlighting. Certainly shows up in natural language processing, shows up in network protocols, shows up in command line languages. So like if you pull down a console in a game like Quake, or if you're typing in a shell, you're typing out some little command language that has to be parsed. It shows up, albeit awkwardly at times, in configuration files. It shows up when we serialize application state or objects to disk. It shows up in query languages. If you put a little search box at the top of your site and you come up with some sort of ad hoc way of parsing that, then you're doing some sort of parsing right there. It shows up, and it also shows up in a roundabout way in API design. So if you're building a library for something or designing an API, you can interpret the procedures in that library as tokens in some grammar. And very often there are ordering constraints on the way in which you can make calls to that library. And those ordering constraints define something like a context-free grammar most of the time. So what I'd like to do now is pick on several of these what should be application areas but are not application areas of modern parsing technology. And I'll start with network protocols. And what I want to do is go through 3 of these and just try to figure out why we're not using the modern parsing technology and what happens as a result. And then ultimately what we can do to fix that. So if you look at RFC 2616, which is the standard, which is the definition for the Hypertext Transport Protocol, otherwise known as HTTP, right at the start of the spec, you're going to find a definition for augmented Backus-Naur form. So they define the mechanism by which they define the mechanism right at the start of the spec. And then all throughout the spec, you just see grammars all over the place. So, what you have is a formal and rigorous way that pins down the meaning of this protocol down to the last byte provided for you in the spec. So here's a grammar. This is a great opportunity for using parsing tools. In RFC 3501, otherwise known as the IMAP protocol, again, in the back, there's a section called formal syntax, which is page after page after page of this formal grammar that, once again, is pinning down to the last byte a formal and rigorous definition of all the messages exchanged between the client and the server. This is the kind of thing you could adapt and give to something like Lex or Yak, if you wanted to. And then if you look at RFC 2812, which is the definition for IRC, once again, more grammars. In fact, for almost any RFC you pull up, you're going to find something in augmented Backus-Naur form pinning down the meaning of all these messages being exchanged down to the last byte. And so we have the formal grammars. We have plenty of efficient parsing techniques. We have stuff like LLK, LRK, LALR1. There's lots of technology out there for constructing efficient parsers. We have lots of implementations of these technologies. We have Antler, we have Yak and Flex, we have Happy, Cups, Bison, Ragel, you name it. We have all sorts of ways of taking formal grammars and turning them into fast parsing machines. So, what's the state of the art if you're building a high-performance network daemon today? Well, if you trawl through a bunch of source code, you'll find out rather quickly that it's pointer arithmetic, oddly enough. So yeah, if you look at Apache, it's 2,170 lines of handwritten buggy C. In Lady, it's about 1,200 lines of C. They can do the same protocol in half as much. In the Freenode IRC daemon, you find about 2,000 lines of C scattered all across these source files. I couldn't actually count all the lines of C dedicated to parsing because they're in so many different places in the source code. In the Courier IMAP daemon, you'll find about 2,600 lines of C, again, all dedicated to parsing the messages going back and forth. So what's the result of all of this handwritten parsing, all this pointer arithmetic, all this buffer bumping? Well, it's a heck of a lot of buffer overflows and a heck of a lot of insecurities. So, if you start searching for any of these daemons and then buffer overflow, you'll find tons of them. And sometimes you'll find 3 or 4 just in like URL handling. I mean, it's astonishing how bad people are at writing parsers by hand when they're bumping through an array. But this is what they do to achieve high performance. So anytime somebody says to you they've written a high performance network daemon, you need to mentally translate that into high throughput exploit server. Because that's really what these devices are doing. And this is the part that really frustrates me. Because if you look at the source code, you will find that they have actually used Lex and Yak in every single one of the programs I just used. But they're not using it to do protocol parsing. They're using it for config files. So it's clear that the tools exist, and the people who write these things know how to use the tools because they use them, but they don't. So why aren't they using them? Now, I'll get to why I think this is true, or why I think they're not using them in a second. But let me pick on something else first. So I mentioned configuration files. So the tools on the previous few slides, they get off light because they did it properly. At least they used Lex and Yak to build their configuration files. Not every program does that. And so there's an interesting experiment you can run late at night when you're alone in the dark. You can just try to cat the entire contents of your etc directory. And what you're going to find rather quickly, I mean, it's sort of nightmarish. It's this mishmash of ad hoc, poorly described configuration files. And so the ones up here, I guess, are some of the worst offenders that I could find. These are the least human readable, if you will. And this whole directory, to me, feels like a monument or a tribute to a false dichotomy, that there's somehow a trade-off to be made between human readability and machine readability. But of course, this is absolutely not true. There is no trade-off, or there shouldn't be a trade-off between human readability and machine readability. There is no trade-off. And let me be perfectly clear. The answer is not XML. XML is a compromise to a problem that doesn't even exist. We can have it both ways. And by the way, XML is neither human nor machine readable. Yeah. Anybody who's edited an ANT file, or tried to write an XML parser, even with parsing tools, knows this much. So once again, we have all these tools that are great that would be great for writing, clean, easy human and machine readable configuration files, but people aren't using them. So why is that? So I'll get back to this in just a moment. I have one more thing to pick on, which is syntax highlighting. So, I use both Emacs and Vim. And, the other day I wrote some code like this. I defined a new type, which is count, which is some unsigned int, and then I used count right here. And Vim's like, well, that can't be a type. That's obviously an identifier. So I'm not going to highlight that for you. Now, here's the weird thing. So neither Emacs nor Vim will actually highlight this correctly. Because to highlight this correctly, you have to actually parse the file, because you have to resolve this weirdness with what is a type name. So clearly they're not actually parsing the file. But there's really no excuse for this. I mean, Emacs and Vi have been around for over 30 years, longer than I've been alive, and they still can't parse as you're typing stuff in. It just seems a little bit ridiculous to me. Why on earth is my text editor still not highlighting my source code properly? So I hope what you draw, or I hope the inference you make from this short set of case studies, is that there's a lot of places out there in the world where we ought to be using parsing technology. And there's a very small subset of spaces where we're actually using it. So, why is that? Well, I don't think it's technical reasons. Not mostly technical reasons, anyway. I think it's largely economic reasons that we don't use parsing technology where we should. And I think you can divide these reasons into three categories. The first one is opportunity cost. Second one is transaction cost. And the third one are barriers to entries to using these tools. So let's take each of these in turn and see what we can discover. So by opportunity cost, I mean, if you decide to write a parser by hand, or if you decide to use a parser generator, you must be giving something up. There are clearly things you could do by hand the parser generator is not going to do for you. So it's important to ask what we're giving up by using a parser generator or parsing technology. And there's some myths about what you give up, but there are some things you actually do. So the first thing that's a myth about what you give up is performance. Some people think that if you use something like Yak or Bison, it's actually going to give you a parser slower than what you could write by hand. Now, you may be able to crank out a little bit more performance if you write your parser by hand, but not much. It's probably not worth the effort. And certainly, if you're trying to write something like a network daemon, you're almost completely I/O bound. I mean, if you're writing a web server, CPU cycles are essentially free because you're going to spend all your time, worrying about the network. So even the slight performance advantage there doesn't really matter that much. So I don't really think you're giving up performance. It was true once upon a time that you were giving up thread safety, and that certainly mattered at one point in time. But nowadays, all these tools usually have a command line flag, and if you give it that flag, you get a thread-safe version of your lexer or your parser or whatever it was you wanted. But you are giving up this last item, which is non-blocking I/O. So there isn't currently a way for most of these tools to say, if it turns out you can't read another character off the socket, give me your current continuation, and then whenever there's something ready, I'll start you up again. Currently, they just call read and they block. So if you're writing a web server and you have a blocking call in there, what have you just introduced? You've just introduced a denial of service attack to your web server. So if you've got 32 threads, and each one of those has a blocking call somewhere in there where it's trying to parse your message headers, 32 connections will lock up your server. So any system that has to be deployed in the real world can't tolerate this kind of automatic insecurity. So they're trading, they're making a trade-off here. They're saying, if they write it by hand, they may introduce buffer overflows. In fact, they can be almost certain they're going to introduce buffer overflows, but they're avoiding the guarantee of introducing a denial of service attack. So that's why people writing network daemons aren't using those tools at the moment. So there's also a transaction cost associated to using modern parsing technology. Suppose now that you want to design a configuration file for your program. So you've got to decide on the format for this configuration file. And what you have to decide between is the time it's going to take to set up something like Lex and Yak and the time it would take to hack something together with strtoc. So let's take a look at the workflow for these two tasks. So suppose you decide to do the right thing. You use Lex and Yak. What's this going to cost you? Well, first, oddly enough, first you create your grammar, and then you're going to work your way down to the Lexel specification, which feels a little bit backwards. But you create your grammar first. Then you define the types you're going to need inside the parse tree and for individual tokens. Then you associate these types with individual parse tree nodes and individual tokens. You define your Yak rules. You compile your Yak spec. And by the way, you didn't once have to reference the Yak manual to do this. And you didn't get any problems when you tried to compile it. You got exactly right on the first try. Then you create your .l file. So this is the third buffer open now. You include the header file generated earlier. You define all the states you need. You define your lexical rules. You try to compile it, but it gives you some weird error about YY wrap not being defined. So you go off and you fix that. Again, you do this all without looking at the manual for Lex either. And then you get to call YY parse. Okay, so this is your reward for doing things the right way. It's about 10 steps or something like that. Or you could say, well, maybe I'll just separate the elements in my configuration file with colons or tab characters. And then what do? Well, the first step is you call strtoke, and that's also the last step. So if you're a lazy programmer, or maybe you just feel like you're an efficient programmer, you're going to do the easy thing, and you just call strtoke, and then you're done. So there's a substantial transaction cost to actually using one of these tools. And I think that's slightly ridiculous. But there are also barriers to entry to using this technology in the first place. Even if you do want to go through all that, you actually have to know how it works. In the sense that if you wanted to drive a car, you would have to know how the engine worked to use something like Bison or Yak. And why is that? Well, it's because most of the time things go right, but every now and then something doesn't go quite right with Yak. In the course of any project, something will go wrong, and then you have to get into its guts. And so, supposing, in the ideal case, here's what Yak will do. You give it a grammar, and it takes this grammar and turns it into a black box. And when you're ready to parse with it, you hook this black box up to the input, and you hook it up to some sort of stack over here. And you say, Yak, go ahead and parse this for me. So Yak starts calling out a sequence command. It says, shift a character off the head of the input, reduce according to this production here, replace what's on the top of the stack. And then, after enough of these operations, you end up with your parse tree over on the top of the stack, which is now the only element over here. But it doesn't always work this way. I mean, if you get it to compile, it works this way. But every now and then, particularly if you're a student in my compilers class, Yak will say something like this. It'll say, oh, I compiled it, and I gave you something, you can run it. I don't know if you want to do that yet, because there are 57 shift-reduce errors in your grammar. Or they're not errors, these are conflicts. And I've resolved them all for you by just automatically shifting. So hopefully that's the behavior you wanted. So now, all of a sudden, you actually care what's inside that black box. You don't have to, you have to know more than just what a context for your grammar is. You have to care how the parser works. Okay, so you open the black box, and the black box is kind of big. It's like 5,000 lines. And you navigate your way down to one of the states that seems to be causing problem. You go, oh, yeah, I remember we learned in class how to resolve this kind of conflict. For this, you just add, the associativity and precedence rules. In this case, we just need to say that, multiplication binds tighter than addition. Okay, so one problem down. That's solved. So you rerun it, and Yak says, good. Now you only have 53 shift-reduce conflicts. So go fix the rest of them. So if you're in my compilers class, about 2 days later, say, okay, so students do one of two things at this point. Some of them think, okay, I'm going to refactor my grammar. I'm going to try to come up with an LALR1 grammar that Yak will actually accept. Okay, and then maybe a third of them will say, no, I'm just going to try to beat this thing to death with associativity and precedence rules. And they'll find some magic combination of these things that actually does get rid of most of the shift-reduce conflicts. Now, it may not actually give you the right grammar or the right parser, but the conflicts are gone. Well, except, of course, for one. And, of course, that's just dangling else, or so they hope, which, you can leave that in because all you need to do there is just shift. And so basically, you've got this barrier to entry, which is you have to actually learn how each tool works to use the tool. And there's an implicit barrier to entry that I hesitate to even mention, which is that, if you're programming in an obscure language, there probably isn't parsing technology out there to help you to begin with. So it helps if, the Lex or the Yak equivalent exists for the language you're programming in, because if it doesn't, obviously you can't use it. So I think most of what I described are non-technical reasons for why people don't use modern parsing technology in all the places that they should be using it. So the question I've been trying to answer lately is, how do we change that economics? How do we change these costs associated with parsing? And I think there's a number. So I'm actually not the first person to realize that parsing is insufficient. So this list I've got here is actually adapted in part from work that Trevor Jim, Yitzhak Mandelbach, and David Walker presented at Popple 2010 last year. And I've broken it into two chunks. For what I think we need to do with modern parsing technology or add to it, and what I think would be nice. So here's what we need. For starters, we need non-blocking I/O. I think it's long past the time where we had the ability to somehow stop a parser, get its continuation, and do something else while we're waiting for more input to come through. I think it'd be nice if, at the very least, parsing technology acted as a library within a language. So this is partly solved by some of the parsing approaches out there today. There are a lot of parser combinator libraries for many of the modern languages out there. Yeah, certainly not any of those for a language like C yet, but they're appearing. But most of the heavy-duty stuff, it doesn't appear in library form yet. We need to be able to handle every context-free grammar because students and the average programmer, I mean, good programmers can understand how to resolve shift-reduce conflicts correctly. They can understand how to refactor a grammar. Not everybody's that skilled, and so we have to be able to handle any context-free grammar. And if they give us something ambiguous, we should just give them back a parse forest. And they can look at the parse forest, they can look at the 2 different trees, or 2 or 3, however many they got back, and they can say, oh, now I see why my grammar is ambiguous. I think I see how to fix this problem. We ought to draw on regular expressions. Most programmers know how to use regular expressions pretty well. So we ought to allow stuff like Kleene star, Kleene plus, question mark, all the other stuff we're used to seeing in regular expressions. We should allow that. And if possible, and I think this is the route that Perl 6 is taking, you can even think about merging your regular expressions and your parsing technology together into one unified whole, so they don't have to learn 2 separate systems for it. I'm not sure that's the best approach, but I think it's one we should certainly consider taking. I think if we want to do stuff like syntax highlighting, we need the ability, again, this is related to the first point with non-blocking AI, we need the ability to sort of capture the state of the parser at some point in a persistent way and tag it to a particular character in the input to say, this is the state of the parse at this point in the input, and if you go modify this character, restart the parse here, and you re-highlight the rest of the file. And we can even make it so that it's possible to try to maybe tie it back together with later parses if we can. So we don't have to reparse the entire file every time. But at least being able to cache the state of a parser at every single character would be useful. And finally, it has to be easy to implement, because if it's not, we'll end up in these weird cases like with VimScript for these obscure languages where we don't actually have the parsing tools yet. So we need something that's easy to implement, that's something that anybody could do. So for the would-be nice stuff, I think it'd be great if you could modify the grammar on the fly. Imagine the scripting languages you could build if, as part of the scripting language, you could tell the parser, reparse this stuff this way now. If you had first-class access to the parser, new kinds of programming languages would be possible. I think it's important to go a little bit beyond context-free languages. So, there's stuff like, there's what I'll call context-dependent parsing, which you run into in things like when you're parsing type identifiers in C. So if we can go beyond context-free languages, that would be great. Even better than having it as a library would be to build it into the language in the same way that regular expressions are currently built into languages. That would be ideal. If you just had slash, then your grammar, then slash, that's perfect. And it should support compositionality so that we don't need separate tools to do lexing and parsing. We should be able to define our lexer with the same technology we use to define our parser, and then plug them together. And if we want to have it 2 or 3 layers deep, it should be easy to have them 2 or 3 layers deep. So I contend that parsing with derivatives can get us everything on these lists, and that this may open the door to parsing in domains where it's not traditionally been used. You're probably thinking at this point, what are derivatives doing in a parser? And the answer is, well, they're not the derivatives you know and love from freshman calculus. These are a slightly different kind of derivative. Now, I'm told there's a relationship, but I think it's somewhat tenuous to the derivatives you know and love from calculus. But I'll go ahead and explain exactly what the derivative of a regular expression is. And as defined in the original paper by Brzozowski in 1964, I think regular expression here is probably not the right term. I think what he really meant to say was regular language. Now, of course, regular expressions are the pattern language for regular languages, but I think it's important to notice the distinction between the two. So keep in mind that a formal language is a set of strings. And so what we're going to be defining the derivative with respect to is sets of strings, not necessarily with respect to a particular pattern language, although of course you can lift it up to that. So regular languages, to review, have sort of 3 atomic languages out of which you construct everything. You have the null language, which contains just the empty string. You have single character languages, which contain 1 character each. And you have the empty language, which contains no strings at all. Then the 3 regular operations you apply to these languages to build them up are union. You just take two sets of strings and union them together. Concatenation, where you have a set over here and a set over here, and you take all the strings in this set and all the strings in this set, and you compute every possible permutation of them. And then you have Kleene star, or 0 or more repetitions of a language. So if you Throw these three operations together, you get the entire class of regular languages. So if you're used to thinking of regular expressions in old Unix or Perl terms, an expression like this becomes this in the language theoretic or set theoretic notation, so that it's a set containing foo and bar with a Kleene star operator attached to it. So now that we've defined, or redefined regular languages and defined languages to be sets of strings, we can talk about what the derivative of a language is. So Brzozowski defined it to be what you get. So if you want to take the derivative of the language L with respect to C, you take every string in that set that begins with C, and you chop off the C. And that gives you a new set, which is the derivative of that set with respect to C. So I tend to think of the derivative in set theoretic terms in two phases. The first phase is a filter phase. Again, it's a set of strings. You look through, find every string in that set that starts with C. And then the second phase is to chop the C off the start of all those strings. So the derivative is not a particularly complicated concept. It's pretty easy to understand. So let's just look at a few examples. So if we have a set containing foo, frac, and bar, and we want to take the derivative of that set with respect to F, we find all the sets containing, all the strings that start with an F, which are foo and frac, and we chop the F off those. So we're left with oo and rac. And if we want to take the derivative of the same set but with respect to B, there's only one string in the set that starts with B, that's bar. So we just chop the B off that, and we end up with a singleton set containing R. If we want to take the derivative of the set with respect to X, nothing in the set begins with X, so we just end up with the empty set. It's not a complicated concept. It's a little trickier when you try to lift this to infinite sets. So here's an infinite set of strings. It's foo or bar star. But it also has a derivative, and we can define it in terms of regular expressions. It's oo concatenated with foo or bar star. Similarly, we can define, or we have a derivative for this set. So it's the derivative of foo or bar star concatenated with frac with respect to F. This one's a little bit trickier because it turns out this first element can be the empty string, which means the derivative might have to jump over and hit the second element. But we can still define it entirely in terms of regular languages. We have oo composed with foo or bar star composed with frac, or just rac. In the case where, so that rac is in the case where it jumped over and just tagged that rac, or tagged that last frac. So there's one important observation that enables you to use the derivative of regular expressions to do matching on regular expressions. And that's that if you have a string in a language, if you pull the first character off that string and use it to compute the derivative of the language, then the original string is in the original language if that tail of that string is in the derived language. In fact, it's if and only if. And so this leads to a pretty simple algorithm for matching regular expressions. What you do is you take your string, you take your language, and you slowly chew your way down the string, deriving the language as you go. When you reach the end of that string, when there are no characters left to consume, you just check to see if the derived language, that final language, contains the empty string. And if it does, the original language contained the original string. So let's just run through a quick example here. Let's check to see if foo is in foo or bar star. So first, we pull the first character off foo, F, and we derive the original language with respect to F. We get a new regular expression over here. We derive the next regular expression with respect to the second character in foo, O, get a new regular expression from that. We derive again with respect to the final character in foo. We get another regular expression from that. And at the end, we check, does this derived language right here accept the empty string or contain the empty string? The answer is yes, it does. And so foo was in the original regular expression foo or bar star. So I'll note for this final operation, I had to have a way of telling whether or not a language accepted the empty string. We can do this by computing what's called the nullability of the language, which actually just tells you whether or not the empty string is in the language or not. So we use this delta function. I think actually Brzozowski used this delta function originally. And when applied to a language, it gives you back the empty string if the empty string is in the language, and it gives you back the empty set if the empty string is not in the language. So this is useful for that final step, but it also ends up being useful for computing the derivative of regular expressions as well. So for the three basic regular languages, obviously the nullability of the empty string is the empty string. The nullability of a single character is the empty set. And the nullability of the empty set is, of course, also the empty set. For compound languages, it has this very nice property whereby it sort of distributes right over them. So the nullability of the union is the union of the nullabilities. The nullability of concatenation is the concatenation nullabilities. And for Kleene star, which by definition always contains the empty string, it's always just the empty string. And what's nice about this is if you implement something like nullability in a language like Lisp, in this case I've chosen Racket, which is my Lisp dialect of choice, it has a pretty compact definition. So it's not a lot of code. It's just a simple recursive walk over the tree-like structure of the regular expression itself, and it computes the nullability for you. So you don't really have to understand the code on the previous slide. I just want to emphasize that the code's not very big. And I'll do that throughout this talk. I just want to emphasize that for the stuff I'm showing you, not a lot of code is involved. So what we want to do now is show that the derivative is closed over regular expressions, and that we can structurally or recursively decompose a regular expression and apply the derivative to its interior. So for the case of the empty set, the derivative of the empty set is obviously just the empty set. There are no strings in it. You're not going to add strings to it with the derivative. For the empty string, the derivative of the empty string with respect to any character is obviously just the empty set, because there's no character to pull off the front here. For the derivative of the character, we have two possible cases. If we're deriving a character with respect to itself, then we get the empty string. But if we're deriving a character with respect to a different character, then we get the empty set. So for union, the derivative of the union works out to be the union of the derivative. So that's awfully convenient. It also turns out that the union of the intersection is the intersection of the derivative. If we're taking the difference of two languages, their derivative is the derivative of the differences. Now things get a little bit trickier for concatenation. So again, I mentioned this briefly when we were looking at some examples, that there's a possibility that this language, this first one, L1, is nullable. And this is what causes all the complication with concatenation. So we've got basically two cases over here to consider. On the left-hand side, we're going to assume that L1 is not nullable. So we take the derivative with respect to C of L1 and concatenate the result of that with L2. Now over here, we actually use the nullability operation. We apply the nullability operation to L1. So there's two things that can happen now. If L1 is nullable, then this right here is going to turn into the empty string, and this whole thing resolves to the derivative of L2 with respect to C. If L1 is not nullable, then this expression right here turns into the empty set, and it annihilates the derivative of L2 with respect to C. So we get exactly what we'd hope for. Now this is something that's unusual. So you typically don't get access to something like complement in regular expressions. But it's very easy to compute the derivative of complement. Actually, for that matter, you don't typically get intersection either. But as I just showed you, it's pretty easy to get intersection out of derivatives as well. But we can also get derivatives out of, or we can compute the derivative of complement pretty easily. And the weird thing about this is, I've proven what the answer is to be true. I understand every step in the proof, but I still don't believe it. It seems a little bit nonsensical to me. But here's what it is, and here's all the steps. So the derivative of the complement is the complement of the derivative, oddly enough. And if you actually use it, it works just like that. And now you can have complement in your regular expressions. And this turns out to be somewhat useful, particularly if you're trying to write a single regular expression that describes comments in languages like C. Obviously, you can do it without it, but it's certainly much easier with it. The derivative of the option is the derivative of the language inside. The derivative of Kleene star is the derivative of one copy of the language pulled out, concatenated with other copies of the language following it. The derivative of Kleene plus is, again, it's one copy of the language pulled out, concatenated with 0 or more copies of the language following it. So it's not Kleene plus following it anymore, it's a Kleene star. And once again, I just want to show that it doesn't take a heck of a lot of code to implement the derivative. This is really all you need to implement the derivative in Racket. And I even added a little optimized case here where I check for nullability. So it could be even a little bit shorter than that. So again, not a lot of code. And so actually, for probably less than 50 lines of code, you can write a general purpose regular expression matcher using something like derivatives. It's quite remarkable. But this isn't a talk about regular expressions. This is a talk about parsing. So we need to talk about context-free grammars. So can we extend the derivative to context-free grammars? So if you're not familiar with context-free grammars, let me give you the short one-sentence version of context-free grammars. I just tell my students that context-free grammars are basically just recursive regular expressions. And that's actually true. It's really what they are. So that if you have a language like this, which is allowed to reference itself or other languages in a mutually recursive fashion, you can describe a language that describes the set of properly nested, the set of parentheses which are properly nested. This actually happens to be a very simple Dyke language, which is an important class of context-free grammars. But needless to say, all you have to do is add a little recursion to other expressions. Now you've got context-free grammars. So can we? I guess the question now is, can we take the derivative and adapt that to context-free grammars? And the answer is yes, we can. It works mostly the same. I mean, it works exactly the same in a mathematical sense. If we're just talking about sets of strings, nothing changes. We're just talking about sets of strings. And you don't have to care how those sets of strings are constructed. The question is, does it still distribute across in the same way? Yeah, and again, it's true in a mathematical sense, but there are some issues here. And you can see them very easily on a language like this. So here's a language, L, which describes lists of x's of arbitrary length. And you'll notice that this grammar happens to be left recursive, but almost any kind of recursion can get us into trouble as soon as we're trying to compute the derivative of context-free grammars. So what happens if we try to compute the derivative of this language with respect to, say, x? Well, in a mathematical sense, again, there's nothing wrong. I mean, obviously, there's still a sensible interpretation to this equation on the board. But if we try to use the same code to compute the derivative of this grammar, we end up with infinite recursion, lots of problems right away, because we try to compute the derivative, we need to immediately compute the derivative of this of the same thing. So we have a problem here, and we'll get deeper into this problem in just a second, because there are other problems here. So actually, here's the code. Here you can see exactly where it happens in the code. So if L1 happens to be the same thing as the input, because we've got a left recursive grammar, then immediately we've got stack overflow if we try to use that old code to compute the derivative. So we're going to have to modify this slightly to fix it. But the other problem is that we need to compute nullability. And this one's a little bit weirder, because to compute the nullability of L, we need to know the nullability of L already. So this is a different kind of recursive problem. It's a little bit trickier to fix, but we can fix this one too. So what's the solution? Well, the solution is three pretty well-known concepts from functional programming. So if you're a functional programmer, it's not too hard to deal with these problems. We need laziness, we need memoization, and we need fixed points. So I'll go through all three, and I'll show you how we adapt the solution to make the derivative work for context-free grammars. So what laziness will do for you is it will delay the calculation of some computation until and when you actually need the value of that computation. So we can use this to get out of this immediate infinite recursion trap, but by itself, it's not going to quite solve the problem for us. Memoization is just a fancy way of saying, the second time you compute a function for the same inputs, just return a cached output. So basically, if you memoize a function, that function is going to start caching all the inputs, caching all the outputs, and any time it sees the same thing again, it's just going to give you the answer it gave you last time. So in purely functional code, this is just a convenient way of optimizing stuff. But as it turns out, it can also turn some non-terminating programs into terminating programs. And then we're going to use fixed points to solve this chicken and egg problem with nullability. So the laziness we have to do isn't that substantial. We don't need to switch to like an entirely lazy language. We just need a small amount of laziness to get around this problem of derivatives trying to compute themselves. So up here I've got the definition of basically what it's a macro definition of a constructor for cat, for the concatenation constructor. And at the moment it's immediately installing the languages it's supplied directly into this data structure. Well, we can't install those languages directly into the data structure because that one of these languages could be the language itself. So we have to somehow insert laziness here to get around the infinite recursion problem. And in a language like Racket, that's easy enough. We just insert delays around this language and that language. And so now, instead of immediately computing L1 and L2, it's going to wait to compute L1 and L2 until these values are actually needed. And once it's computed them, it will also cache them for you. So if these values are ever needed again, it doesn't recompute them. It just gives you the values it had before. So that's all the laziness we need. So you'll notice with just that laziness now, if we did have L1 equal to the input L, this computation wouldn't actually happen yet. Well, what you get with just laziness is basically it's going to dynamically unfold the grammar as it goes, creating what's almost like an infinite tree as it's building up the derivative. Well, we don't want an infinite tree, basically an infinite regular expression. What we want is some sort of finite grammar. We need to actually tie the knots back together. And that's what memoization buys for you. So what we could do with memoization is say, memoize the derivative, so that if you ever see this language derived with this character ever again, don't do it freshly. Just give it back the answer you had last time. Give it a pointer to that old node you already created. And in a language like Racket, it's actually pretty easy to make this change. Instead of saying define, you just say define with memoize, and then you specify the order in which you need to memoize the arguments. So very small change to the code, and suddenly it's now working on context-free grammars. But we have one more problem to fix. So we have this chicken and egg problem where we're trying to use the nullability of a language to compute the nullability of a language. But this is actually already a solved problem. And we know how to compute the nullability of something in a context-free grammar. And we can do it quite elegantly in a functional setting if we apply the notion of fixed points. So basically what we do is instead of saying define the nullability of a language to be this, we say define with fixed point the nullability of a language to be this. And if you to kick off the recursive case, when you need to know what the initial value of the nullability is, start with false. Assume it's not nullable, and then basically iterate over all the nodes in the grammar, computing their nullability until none of the nodes change their value anymore. And once they stop changing their value, then return to me the value you get back for nullability. So with some very small changes, define memoize and define fix, we've taken the derivative which worked on regular expressions to a derivative which works for context-free grammars. So it works, but it's really only for recognizing. You don't match with context-free grammars, you parse with context-free grammars. So what we'd really like to do is figure out if we can adapt them to work for parsers. And the answer is yes, we can actually do this. So first we have to sort of think about what is a parser in a mathematical sense. So a parser is a function that takes in an input string and gives you back a set of tuples, or a set of pairs actually. And each pair in the set contains a parse tree, and it contains the remainder of the input. So this is what I'll call a partial parser. It's taking a string, it's consuming all the prefixes of the input that actually match what it's able to parse, turning those into parse trees, and then giving you back the part of the input it couldn't parse yet. So you're probably more used to thinking of parsers as full parsers, where a full parser takes in an input string and then gives you back just a set of parse trees. So if you're parsing some sort of ambiguous grammar, you'd actually get back a real set with multiple items in it. Most of the time, you'd expect to get back just one parse tree. Or if there's an error in what you're trying to parse, a syntax error, you'd expect to get back the empty set. And there's a way to turn those partial parsers into full parsers by applying the partial parser to whatever the input string is you're trying to parse, and then just pulling out all the parse trees that are paired with the empty string. In other words, all the parse trees which consume the entire input. So there's a relationship between the two. It's important to think of partial parsers, though, when we're trying to define the derivative. It doesn't actually show up in practice. We don't need the partial parser in practice, but we do need it for intermediate proof steps. So now what we need to do is come up with combinators that allow us to build context-free parsers. So if we've got these little atomic parsers, we need to combine them so that we can describe parsers over context-free languages. So we can take any string and turn any string into a parser. So when a string turns into a parser for itself, it consumes some input, and then it checks to see if it's at the prefix of that input. If it's at the prefix of that input, it's going to return a singleton set. And the tree it's going to return is basically itself. It's going to say, I parsed myself. That's me. I'm the parse tree. And then it's going to give back the remainder of the string, whatever was left over after that. Now, if it's not the prefix of the input, it just returns the empty set. It says, I'm not designed to parse this string. This is a failure. We can turn the empty string into a parser, and it's going to succeed every single time. If you give it any input, it's going to consume absolutely nothing and give you back itself as the parse tree. We can also turn the empty set into a parser, which always fails, always returns the empty set. So now we've got three basic parsers, and now all we need is ways to plumb these guys together to get parsers for context-free languages. So if we have two parsers, we can concatenate these parsers together. If we have a parser P, which consumes strings over A, alphabet A, and gives you back parse trees of type X, and a parser Q, which consumes strings over alphabet A and returns parse trees of type Y, we can get a concatenated parser, P concatenated with Q, that returns parse trees that are pairs of x's and y's. So how do we do that? Well, this is probably the most complicated definition I have to go through, but it's worth stepping through to see exactly how this works. This is exactly where these partial parsers come from. So the concatenated parser takes in the input, and then it runs that input through the first parser. So it applies the first parser to the full input, and what it gets back is a bunch of partial parses. It gets back parse trees of type X, and it gets some remainder to the input. So then it takes the leftovers from these parses, and it drops them in to the second parser. So now we get more parse trees and the remainder of the input. So it takes the parse trees it got from that, the x's and the y's, it pairs those together, and then it takes the remainder of the input from the second parse, pairs that with the x and the y paired together, and that's all the those are all the parsing results we get from concatenation. So union, fortunately, is much easier. So if we have a parser that gives you parse trees of type X and a parser that gives you parse trees of type Y, or also of type X, to union together, you take some input in, you parse with the first one, you parse with the second one, you union the results together, and that's it. You've got a union parser. To construct sensible parse trees, you'll also need a reduction operation for your parsers, where you give the parser some function. So if you have a parser that gives you back parse trees of type X, and you have a function that turns x's into y's, you can combine these together to get a parser that just gives you y's. So if you're in a tool like Yak, you often have to write these semantic actions. This is the equivalent of writing those semantic actions. This is what turns the parse tree into something. So what this one does is it takes in the input, it passes that input off to the parser. That parser gives you back a whole bunch of parses where it's giving you x's and the remainder of the input. So we have the function f, which takes those x's and turns them into y's. So we apply f to all those x's, and we get back a bunch of parse trees of type y. So now what we need to do is define the derivative for parser combinators. Previously, we defined the derivative to take you from one language to another language. Now we need to do the same thing, but for parsers. So we can take the derivative of a parser and get back yet another parser. So it's actually not too hard to define the derivative of a parser. The derivative of the parser, with respect to C, takes in some input W. It applies that W with C appended to the front to the parser, and then subtracts off anything that didn't actually need to consume one character of input. Because when you take the derivative, you're sort of forcing one character of input to be consumed, and so we have to subtract those off. Now, the useful thing about this definition is we can flip it around, and we can define the parser in terms of the derivative. And this is the first step towards getting an algorithm that will allow us to compute parse trees using just the derivative instead of actually running the parsers. So to parse some string, so to parse a non-empty string, if you will, you pull that first character off, you take the derivative of the parser with respect to that character, run the rest of the input through that string, so now you do the parse of that, and then you add on anything that wasn't required or that was able to parse with just the empty string. But of course, we don't actually have to do this most of the time in practice. In practice, we're not typically concerned with partial parses. We're typically only concerned with full parses, where you consume the entire input all at once. So we typically don't care about what you can get by consuming nothing right up at the start. So most of the time, we want a parser that looks like this, a full parser where you give it a string CW, and it just gives you back all the possible parses of CW, never minding the empty parses. So this is the definition. This is how you actually do parsing with derivatives. This is how you can get one step forward by computing the derivative. And then you can just take one step forward after that, and so on all the way until you're done. So now what we need, just like we had with regular expressions, is a way to show that parsers are essentially closed under the derivative. And we can push these derivatives deeper and deeper into the structure of the parsers until we finally, at the end of the day, get our parse trees out the other end. So the derivative of a single character is, and all this, of course, is analogous to the derivatives we had earlier. The derivative of a single character, if it's the same character, gives you back something like the empty string, but it's the empty string reduced. We actually have to remember that at this point in the parse, we actually saw a C. And so we introduced this reduction to do that. So we have the empty string that comes out, but the empty string gets reduced so that when it takes in the empty string, it gives you back the character that was parsed. So what's basically happening here is as you're chomping through your grammar with derivatives, the grammar sort of goes into this hybrid state where it's partially representing the parse tree and partially representing the rest of the grammar. And then by the end of the parse, your grammar has transformed itself entirely into just the parse tree. Now, if you're taking the derivative with respect to a different character, obviously that's just the empty set. The parse has failed at this point. So the derivative of the union of two parsers is the union of the derivative of those parsers, more or less as we'd expect. If we take the derivative of the reduction, we're taking the reduction of the derivative. So again, the derivative just has, for the most part, except for concatenation, these very clean properties, where it just distributes right across. Now, if we're taking the derivative of concatenation, things are a little bit more gruesome. So the easy case is where that first language, the first parser, never accepts the empty string. And if that's the case, all we have to do is take the derivative of the first parser and concatenate that with the derivative of the second parser. Now, if that's not the case, we have a little bit more homework to do. We have to take the derivative of the first parser, concatenate that with the second parser, and then account for the case where we jumped across and started taking the derivative of the second parser. But there could be information inside that first parser that we need to remember. We have to actually parse that, get the null parse for that first derivative, or for that first parser, and concatenate that in a reduction with the second parser, or the derivative of the second parser. So that if there was information about the syntax tree down there, we don't lose it by throwing it away. And when you're taking the derivative of context-free grammars, you can throw this information away. But now there's actually information about the parse living inside there, so we have to keep it around. So what does all this look like in code? Well, fortunately, it's not that much more complicated. So here's the derivative. Here's the definition of the derivative of a parser, again in Racket. And what you'll notice, it's not that long. And again, I've even inserted a few hand-optimized cases in here, so it could be even shorter than that. So not a lot of code, but an awful lot of benefit. Here's the definition of what I'll call the parse null procedure. So previously, we had to check to see if something could be nullable. Now what we need to do is actually construct the parse tree for when all it consumes is the empty string. And that's what the parse null procedure does. So it has the same structure as the nullability procedure did. But what it's doing now is building up sets of parse trees when all you consume is the empty string. But it does it in exactly the same way. It's using define fix in the same way that nullability used define fix. Now you're probably wondering, what's the performance of all this stuff? Does this actually work in practice? The answer is it's pretty atrocious. If you actually run this stuff, it's a total disaster. We can fix that. But let me just show you how bad it gets. So basically, as you start deriving your way through the string, the size of the grammar grows almost, actually it does grow exponentially. It just gets really big really fast. And this is bad because the cost of the derivative is proportional to the size of the grammar in the worst case. So you can't get too far before you basically run out of memory with this approach. So in the complexity, because you can double the grammar with each derivative, is definitely exponential. It's the cost of each derivative in the worst case by the time you get to the end could be 2 to the n times, where n is the size of the input, times the size of the initial grammar. And you pay that cost n times in the worst case. So that's bad. Now, I can try to give you a sense of why it's bad by looking at an example. So up here, I've got a grammar actually defined in my Lisp implementation. And what I'll do is I'll take you through several derivatives of it. Really, I'll show you a visual depiction of several derivatives so you can see why it's exploding. So this language is called oneList, and it's just a list of ones. It's an arbitrary list of ones, or a list of arbitrary length containing nothing but 1, 1, 1, 1, 1. And what you'll notice up here is that it's left recursive. So left recursion, in this case, is actually a really bad thing. Left recursion causes lots of problems for the derivatives approach. But it turns out that with some fixes, left recursion actually works better than other forms of recursion for defining lists. So let's see what happens if we take derivatives. So here's a graphical representation of this grammar without taking any derivatives. This is the grammar itself. So you can even see the structure in here. At the top level, it's a union. It's got a concatenation on this arm, where the left-hand side is the language itself. This is the left recursion right here. On the right-hand side, it's just a 1. And then in the other case for the union, it's just the empty string. Okay? So here's the grammar after 1 derivative. It's getting a little bit bigger. Here it is after 5. And here it is after 10. So the size of the grammar grows pretty fast. So that's the problem. So what we need is a procedure to compact grammars back down, because if you spend a lot of time studying the kinds of graphs I just showed you, you realize that there's an awful lot of redundancy in them, a lot of stuff that doesn't need to be there. So we've got this compaction procedure that uses rules like this. There's about 15 rules that look something like this, where if you've got a parser that's concatenated with the empty parser, obviously that's just the empty parser, so you can just cancel it out and get rid of it. So we need lots of rules like this. And I think this is probably one of the more important ones, which allows you to turn a concatenation with a reduction into a reduction with no longer any sort of concatenation whatsoever. So this is an important rule for eliminating lots of the empty strings that are with little parse trees attached and that show up all over the grammar. So this is what compaction looks like in practice. It's got exactly 15 rules to it. And to make it work in practice, we can't just apply these rules at a top level. We actually have to apply these rules deep and structurally to every part of the grammar. So we actually memoize compaction so that if we come back to a node that we've already compacted, we don't try to recompact it again. We just use the first compaction. So we're using memoization to tie these knots. And now, if you take the derivative of that one list language from earlier, this is what it looks like after one derivative. This is what it looks like after 5. And this is what it looks like after 10. So the grammar actually isn't changing in size at all anymore. It's staying roughly the same. So if you look at the size of the grammar over time with respect to the number of derivatives with compaction enabled, where basically every step you compact the grammar according to these reductions, you get this little sawtooth pattern to the derivative. So the grammar grows and shrinks and grows and shrinks and grows and shrinks over time, but never by very much. It stays roughly in the ballpark of its original size. And that's interesting, because if that's the case, if it's always going to stay roughly in the ballpark of its original size, then the average complexity is roughly linear, where it's the size of the input times the size of the grammar. Because again, you're taking n derivatives, and the cost of each derivative is proportional to the size of the grammar at that point in time. So again, if you're staying within a constant factor of the size of your original grammar, it doesn't cost that much. So let's see how we did with derivatives in terms of what we need out of a parser. So I said we needed non-blocking I/O. So can we get non-blocking I/O with derivatives? Yes, we can. Because it's very easy to see how to get the state of the parser after you've consumed one character of input, because that's basically what the derivative is. The derivative is computing the continuation of a parser. That's really all it does. So we've got that. So can we build it as a library within a language? Well, yes, I've done that. I've got the code for it. It works quite nicely in Lisp. Can it handle all context-free grammars? Yes, it can. If you give it an arbitrary context-free grammar, you get back a parse forest. If you give back an ambiguous context-free grammar and you give it to an input where there are multiple parse trees, you get all those parse trees back. There's even a way, using functional programming techniques like laziness, to get a lazy parse forest so that you get not all the parse trees back all at once. You can say, just give me the first one. If I want another one, I'll ask for another one. So that way you don't pay the full cost of all the parse trees. It does draw on regular expressions. You can use regular expression notation for describing these things. Notation, or I guess regular expression operators, the kinds of stuff people are already familiar with. You can cache partial parses in the same way that you get non-blocking I/O. If you want to parse your way through an editor, getting a parse at every single point so that you can resume the parse if somebody makes an edit to the file, you can cache whatever the derived language is, or what the derived parser is at that point in time. And I think it's reasonably easy to implement. Even with the implementations of define fix and define memoize included, it's still under 200 lines of Lisp. So it's not a whole lot of code. And we've implemented it in several other languages, and it tends to be a little bit bigger in some other languages, maybe a little bit smaller in some others, but it's still well under 1,000 even in languages like Scala. So then I had this list of stuff that would be nice to get from parsers. So we should check to see if I can get these as well from derivatives. So derivatives don't pre-compute anything. So if you want to go and modify the grammar right in the middle of the parse, you're more than welcome to do that. You can jump right in, change a rule, add a rule, delete a rule, doesn't matter. And because we don't have any pre-computed tables, because we're basically amortizing the cost of their construction in some way, you can change the grammar. So if you want to write a scripting language that allows the user to change the syntax of the language as it's being interpreted, you could do that with derivatives. No, nothing wrong with that. Maybe that's a dangerous thing. You think of some awfully obfuscated code you could write with that kind of power, but the right people will hopefully find and use that technology. Did we go beyond context-free languages? Well, yeah, we did, because you get stuff like complement. But it's also easy to add these interesting little context-dependent rules that you can also distribute the derivative across. So actually, I don't know the full expressiveness of the derivative. I don't know what the full I don't know where you cross the line into incomputability with the derivative. But certainly you can take the derivative of stuff like context-sensitive grammars as well. I actually, with the list version at least, I defined a bunch of macros that built it right into the language. So it feels like it's a native part of the language. It has its own little sub-language syntax for describing grammars. So we got that. And it certainly supports compositionality. You could have a list coming out of one, turning into a tree in the other. You could have a list going into a list. So as it turns out, some languages like Python are easier to lexically analyze if you do sort of two-phase lexing. Some languages like C, you have the pre-processing phase. You can imagine that as a separate lexical analysis phase. It's certainly easy to compose these things together. So it seems like we got that too. And at least in our experiments so far, it also seems to be reasonably efficient as long as you throw in stuff like compaction. So if this sort of stuff interests you, there's a little further reading you can do. There is quite a gap in the literature, though. So there's the original paper back in 1964. And then nobody seemed to remember what derivatives were till about 2010, when the next paper appears. So the Owens, Repi, and Turon paper is in the Journal of Functional Programming, talks about doing lexical analysis with derivatives. So they revisited the whole idea and found that you can do much better than modern lexical analysis tools if you actually go back and reuse the derivative. There's a really cool paper at ICFP this year by Danielson, where he used the derivative to prove the totality of parsers. So he could prove that parsers would terminate using the derivative. And then we have when I say we, I mean myself and my undergraduate student David Duraeus have a paper on archive you can read called Yak is Dead, which describes most of what I just showed you right here. So if you'd like to know more, there's also all the code for everything I just showed you available on my blog. You can download it. You can play around with it. Other people have implemented it in other languages. If you implement it in a new language that hasn't been done for before, please let me know. I'd like to play around with it. But other than that, thanks for listening. And if you have any questions, I'd be glad to take them.
A lot of the benefits you were getting, like usability as a library and composition and first-class language features, seem to be because you were implementing it in Racket. So, like, how does this help someone in C, or alternatively, like, how does this improve on something like Parsec, which already is first-class library feature, is type checked by Haskell's type checker and all that stuff?
Right. So yeah. So yeah. In functional languages, the situation isn't so bad because generally you do have these common data libraries. Some of the common data libraries I've played with don't support arbitrary context-free grammars. At least that's been my experience. I can't remember if Parsec does or doesn't. I know with Happy, the parser generator, you can get like full GLR parsing, but then you have to run the separate tool. Do you know if Parsec gets you full CFGs? Okay. Yeah, I don't think Parsec works on full context-free grammars. I could be wrong, but last time I played with it, I think it couldn't do stuff like left recursion.
What do grammar definitions look like?
What do grammar definitions look like? Let's see. At the moment, they're not the prettiest, but they're not too ugly because they're just they're just Lisp code. So there's a lot of parentheses involved. Actually, let me while this is up, let me show you the definition of define fix. So this is the start of define fix, and that's the bottom of define fix. So it's not too bad. It's sizable. It takes advantage of some pretty bizarre features, but it actually works. Yeah. Let's see.
How will BNF look like?
Let's see. I might be able to just find a grammar down here. So I haven't actually written a lot of grammars with this yet. So here's a grammar for a left recursive list. So it's not terribly pretty, but if you wanted to define a BNF-like format, you could. I haven't spent a lot of time making it pretty yet, but that's what things look like. Let me see if I can find the expression grammar. Thought I had an expression grammar in here somewhere. Yeah, it's just sort of a mess at the moment. Oh yeah. Here's a really toy expression grammar. So like, here's the pipe from Yak, and you specify that now it's a sequence. So you're basically saying it's S is it's either an S plus an S, or it's a 0, or it's a 1, or it's an N. Yeah. So it's not the prettiest version, but it's maybe about the same as Yak in terms of prettiness, which isn't so pretty itself. And of course, it's all macros, so you can sort of improve it arbitrarily, as long as you're happy to live in this S expression world.
Can I ask you about your comments on XML? Early on you mentioned
Sure.
XML not being a solution. Can you elaborate on that a little? I'm thinking about schema awareness, new features in XML that seem to be very valuable.
Yeah, so my criticism of XML is largely superficial in that I just don't like looking at XML files. I just, it's an ugly format. I think it's a step up in that it's sort of this generic way of describing trees. I think that's great. I think S expressions did it better. Maybe 3 decades earlier. I don't see why we had to go from S expressions to XML. Yeah, it's just that I remember like when students started turning in ANT files to build their projects instead of make files. That was a pretty depressing day because I went from being able to understand what they turned into this incomprehensible mess of tags, and so I miss stuff like make. Yeah. Yep.
So if you were doing a production compiler today, would you choose this as your potential as a parsing technique?
Well, I actually would, but mostly because I want to find out if it's possible. So I'm actually using a compilers class right now, and I'm actually going to use this parsing technology to build a parser for Python. So my guess is it'll work pretty well, and if it doesn't, well, I'll report back.
Well, there have been a number of people that have done precisely that in different contexts. I wrote one 300-line parsing program for Python. After the fact, I'll give you a reference.
Oh, we need to check. Yeah.
But it's very clever. And the fact that the grammar is expressed in part as a regular expression itself is really very, very intriguing from a language design point of view. It's sort of a natural notation.
Yeah. Interesting.
Stupid question. Since you mentioned pretty so many times, how much prettier can you write it, you think? Is it a question how long it'd work out?
How much prettier can I get? Can I make the code or the grammar? Or?
Well, the complicated example, for instance, you showed before.
You mean as how can I keep the grammars looking or the graphs themselves looking pretty? We actually have a working hypothesis, which is that the compaction procedure I talked about will actually give you cubic complexity in the worst case, which is sort of what you'd expect for parsing. And to do that, you have to keep the grammars pretty small and pretty nice looking. So we suspect we can keep just about any grammar pretty looking for some definition of pretty.
Wouldn't you want to create a BNF to grammar parser?
We may eventually, create some tool that slurps in a BNF, or maybe even slurps in exactly a Yak definition or something like that. In general, I don't like doing that because now you've added this sort of extra, transaction cost to engaging with the tool, creating a separate file. And I'd rather just, keep, I don't want the user to leave the buffer they're in. I want them to start writing the grammar right at the point where they need it, so they don't have to switch into a different mentality.
Can't you write grammar for the grammar?
Well, certainly we could. Yeah, so it would be, actually what I started doing last night for Python was, Python has its grammar defined in a formal way, so I wrote a parser for the Python grammar to generate the S expressions I need to apply to my own parsing technology. So
he's already done it. I mean, that's BNF-ish.
Yeah.
That's unlike.
Yeah, so if you're happy with the Python, the way Python defines its grammar, I've already got a tool that translates that into my format, or almost. I just need to make a couple changes to it and it'll be ready to go.
Both the Haskell and Scala version of the parser look great.
Yeah, those are a little bit uglier, but still not too bad. They're still pretty short. And the Haskell one has been substantially improved lately. So the undergraduate that's working with me on this is a real Haskell guru. And he's come up with some pretty clever ways of making, because I think the Haskell version was around 600 lines. I think he's getting it down to about 300 lines now. And the Haskell version is a little bit trickier because it's hard to do stuff like memoization in a purely functional language. There are ways to hack it in, and he's been exploring those too. But the Scala version is reasonably pretty, particularly when you do the operator overloading stuff. So you get the little BNF style : equals. Yep. Mm-hmm.
How does the performance of this parser compared against the standard parsers?
I don't know, but I assume it's going to be a little bit worse, actually. So if you take a parser generated by Bison and compared it to this, there's a lot of overhead that's destroyed when you generate these parsing tables statically. Whereas we're, in some sense, amortizing the cost of constructing these tables. So I don't think we're going to be as fast. But in stuff like compilation and stuff like network protocols, the performance bottleneck hasn't been parsing since maybe the 1970s. If you're doing compilation, the bottleneck is definitely in static analysis. That's where all the hard stuff happens. So if you take an extra second for parsing, I don't think that's so bad. And again, for network protocols, it's a totally I/O-bound process. Again, CPU cycles are essentially free. So if you spend a little extra time parsing stuff, I don't think it'll be so bad. I actually have built a web server based on derivatives, and it's an elegant way to write a web server. The code just looks beautiful, and it seems to get reasonable performance too. It was 800 lines. Yep. So one more question.
It would be hard to deploy this in the core routers where they need to do a little bit of parsing.
To apply it where?
In the core routers, for example.
You mean like the big iron, routing tons of traffic? Yeah, well, there hopefully everything's baked into silicon there. Hopefully you're not running much software to do real routing. Yeah. Yeah. But actually, maybe you could use derivatives to compile that to FPGAs or something like that. That would be neat.
We, the simple people, did a compiler in hardware, so this is no problem. So using these formal techniques, what are the properties of this technology?
We can prove that it's possible to use things like complement, which typically, Yak's not going to give you complement. We can give you complement. So that's one thing we can prove that, or I guess give you that some stuff like Yak can't get. It's not a theorem prover, so it's not like something we can prove about a program with this that standard technology wouldn't give you.
Do you think the derivative for regular expressions is a practical way to regular expressions as opposed to useful automata?
I think it is actually. I think even dynamically computing them is a reasonable thing to do because it's 2011 and hardware's pretty fast now and memory's pretty cheap. I've implemented libraries this way and I've never once had a performance problem. When you get to the pathological expressions like dot star 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 with an X on the end, it's going to blow up in the same way the other tools are going to blow up on you. But I think it's a perfectly reasonable way to do it. It's certainly a great way to do it pedagogically. If you want to teach a student what a regular expression is, you could like for a simple homework assignment, you could say implement a regular expression matcher, and they can do it in not a whole lot of code using techniques like this.
For more, please visit us at stanford.edu.